Starting now this lecture. Good afternoon. On behalf of Indian Aerosol Science and Technology Association, I welcome all participants who have gathered to hear this important talk by Dr. Pratim Viswas. ISTA's efforts to provide a framework to share knowledge and experience via monthly online lecture series has reached to its half-yearly stage. This online lecture series has been initiated to benefit Indian researchers, and we are very much sure that we are on the right path moving as per the mandate of ISTA. We are just 2 months away from our national conference as well, and I take this opportunity to apprise you all that we have received a great response from all stakeholders for the upcoming conference. I am hopeful that many of you will come to Mumbai during 12 to 14 December and become part of this conference in person as well. Today's lecture has a special significance for ISTA. Dr. Pratim Viswas, who is a well-known scientist, also an ISTA member, has always been a contributor to ISTA's imprints. We thought hard to get someone who can introduce our famed speaker appropriately for today's lecture. And finally, we zeroed on Dr. Y.S. Maiya. Dr. Maiya has worked intensively for the foundation as well as expansion of ISTA as well, apart from his scientific endeavors. Sir, it is my humble duty to invite you now to introduce Dr. Pratim Viswas. Dr. Maiya, please.
Thank you, Dr. Manish. Good afternoon to everybody, ISTA members and other colleagues. It is indeed a pleasure, a great honor of no small measure to have this opportunity to introduce Dr. Pratim Viswas to the modern day ISTA audience. Modern day because otherwise, as Manish mentioned, Professor Viswas is no stranger to us. He has always been associated with the Indian aerosol community in general and ISTA in particular for decades. I knew him since the early 90s when he used to visit Baba Atomic Research Center under the invitation of Dr. U.C. Mishra and Dr. P.V.N. Nair and deliver lectures there. The ISTA community, particularly Professor Chandra Venkatraman, Dr. B.K. Sapra and myself, owe to the support of Dr. Viswas, the presence of Professor Sheldon Friedlander and the huge international participation we received in the Asian Aerosol Conference that was organized in Mumbai in 2005. It is no exaggeration to say that Professor Viswas, who started his journey as an aerosol researcher in the US after graduating from IIT Bombay in the 1980s, is among the most prolific, dynamic, and most highly reputed aerosol scientists in the world today. He is the Dean, College of Engineering at the University of Miami, and professor in the Department of Chemical, Environmental, and Material Engineering and Atmospheric Sciences. He is a visiting professor, Washington University in St. Louis, where he was associated before moving to Miami, and was the Lucy and Stanley Lopata Professor of Energy, Environmental, and Chemical Engineering. He is a member of the Global Center for Aerosol Science and Technology, CAST, a co-founder of 2 startup companies, and holder of about 12 US patents. At the present, Dr. Viswas directs the Aerosol and Air Quality Research Laboratory, and perhaps there is no area of aerosol science and technology that he has not covered. From air pollution to bioaerosols to reaction engineering to nanoparticle technology to aerosol fundamentals. This he has achieved through a staggering output of 465 refereed journal papers, along with graduating 64 doctoral students. He is the recipient of many national and international awards. In particular, he won the International Fuchs Award in 2018. It is given to an outstanding aerosol scientist selected worldwide. This is the highest award for any aerosol scientist can aspire. In 2019, he was elected to the prestigious US National Academy of Engineering. On a personal note, I had the pleasure of participating and witnessing a great gathering of aerosol scientists in the International Aerosol Conference organized by Dr. Viswas in St. Louis in 2018 as a conference chair. IIT Bombay, particularly Department of Chemical Engineering and Center for Environmental Science and Engineering, will remember him for his initiatives in establishing academic programs with US universities and for delivering a series of lectures in our GYAN program. Dr. Viswas is an accomplished admirer of aerosol discipline. I've heard him several times, enjoyed his lectures. He is a forceful enunciator of the idea of aerosol science as a great enabler of sustainability. We are very fortunate to have you, Dr. Biswas, here and listen to your current exposition on the subject. I welcome you, Dr. Biswas, to share your thoughts with us all, particularly with the new generation of IASTA members. Dr. Biswas, please deliver your lecture now. And
Good.
thank you for accepting our invitation. Yeah.
Sure. Thank you so much, Dr. Maya, for those very kind words.
The pleasure.
The organizers, Dr. Manish, Dr. Rastogi, thank you for inviting me. It's always a pleasure to connect to IASTA. As Dr. Maya said, it has been a great pleasure to be connected, and would love to see a lot more growth in the field. And my talk today will sort of refer to that too. And we all like acronyms, so I just came up with this new one, the field of aerosol science and technology. So I will be speaking in a little broad sense, but of course, due to limited time, we'll just touch upon one or two things. The field is just fascinating. Dr. Maya mentioned one of our pioneers, Professor Sheldon Friedlander, who also visited India, in fact, shortly before his passing away. So it was a great pleasure to also have him there. And he sort of coined this term that it is really an enabling discipline. So I'll sort of try to relate to that. And somehow this is, I might have to go out and come back. Excuse me. The slides don't change sometimes. And I hope you can see my slides.
Yes, we can.
Okay, so we start with acknowledgements. While I stand here and or comfortably sit here and give this presentation, it's the work of all my students who really have kept me motivated, have in their own right done excellent work. I think some of my current students woke up early to listen, and thank you so much. And I have had the privilege of working with some excellent colleagues. Professor Maya is one of them, Chandra Venkatraman, and many others now with my former students, Professor Sahu, Jay Prakash, I noted is also on, and young faculty members. It's always a delight. I have to acknowledge the funding agencies that have kept the work going, supported the scientists in the group, which allow us to do that. So this is the outline of my presentation, and I will just start with maybe a simple way. What exactly are these aerosols? You know, it still is a sort of very specialized topic, though it is so prevalent. And some of you are leading experts in the field, so please bear with me as I go into a very simple format. I hope there are some students, and I hope you appreciate that, which will also then allude to the importance of the fundamental phenomena. And it's such a fascinating field, and was really in the forefront about 150 years or so ago, maybe 200 years ago, that had led to a lot of developments. And the history of the field itself is so fascinating that it really gives us the motivation to work on this. I'll talk about the governing equation, try to package all the sort of phenomena and focus more on the physics. In parallel, there's very exciting chemistry that happens, which I won't get into, of course, adds to the complexity, but I'll just focus on the physical phenomena and then the challenges in really dealing with this equation and the governing equation. And now, of course, you know, the field of generative artificial intelligence, the concepts of machine learning, which have been used in some way for many years, but now the term has come to the forefront. And of course, we rely on that too. And then I'll cover a few application areas. And for some reason, this thing gets blocked. I don't know. I'm sorry, I have to keep going back. Maybe it is this. Sorry for these technical difficulties. So the word aerosol itself, it's a suspension of fine solid or liquid particles in a gas. It has the Greek origin. And you know, the Greeks were at it, along with, of course, even historically, many of our Indian scientists were at it. And there was tremendous cross interaction between these communities. But of course, the term comes from the Greek origin. But we have to really delve in deeper now. What exactly is a particle, right? So I'll just use a simple definition. It's a stable cluster made up of molecules and sometimes of atoms. If I have an elemental species like carbon, pure carbon or pure silver, then of course we refer to those as atoms. But it's a stable cluster. The reason I mention this is, what is a gas? Because the stable cluster is suspended in a gas. A gas is also made up of molecules, but it is an ensemble. It's not clustered. It's not stable. And this is extremely important in really bringing the exciting physics into the situation. So I'm going to delve into that a little. I hope you can see particles in a box. And these little blue things are gas molecules. And then I've sort of represented a stable cluster of two particles. I'm just showing that this is an illustration. And you see that in this box, there are molecules. There's a gas, right? I could, of course, remove all the molecules. Then I have a vacuum system. And I just mentioned that in passing because now today, and it was very exciting to see even the moon lander. And if you think about the moon is literally a vacuum, right? So there are no molecules. Then what happens to the particles? But the lunar dust is such an important factor. So the practical applications are tremendous. But let's come back to a simple box. Shown here are two particles. Of course, they are stationary as I've shown them. But these molecules, if you note, are going and hitting this particle, and molecules always move around. Now, are the molecules, which is the gas, a stable cluster? If you notice carefully, maybe I stop and freeze this. I do see that there are clusters of molecules, but it's not stable. Another snapshot and the molecules come apart, whereas the particle retains its stability, right? Now, the particle could also break apart, but I'm keeping my particle intact. So that is the difference. And the interaction of the gas molecules with the particle bring these fundamental behavior into the forefront, right? So a little more to talk about that. These molecules move really fast. And, you know, at least I put on an engineering or a quantitative hat. I really love numbers. And I say fast. What is fast? Maybe I drive my car fast, but I'm nowhere near 300 to 400 meters per second, right? So it's really a high velocity or high speed. You can look at how fast do we move, and I'll pick the fastest human on this who used to be here, still here, but doesn't run anymore, Usain Bolt. He runs 100 meters in less than 10 seconds. So about that's 10 meters per second. So look at the order of magnitude. These are really moving about fast. And as they move about, another thing to note, do they move at different velocities? Yes, depends on the temperature. Unless the temperature is 0 Kelvin, these things are always moving. Now, we might be interested in 0 Kelvin and really freeze these molecules to understand behavior, but we are also practical. At least today, I'll be looking at real systems. I'll look at the atmosphere, and this is a typical velocity of my molecules. Do particles move? I haven't shown them to be moving. Remember Newton's laws? You know, whenever there is a force acting on something, it moves. And when these molecules bombard this particle, it brings in a motion. That's one way of moving particles. The interesting thing is when I am at a non-zero Kelvin situation, I'm always imparting a force. So my particles are always moving too. How fast are they moving? Maybe not as fast as the molecules, but the gas molecules, but definitely they are moving. Okay, so this brings in some of these interesting things. Let's bring the concept of size now. I mentioned size, a particle is large. I start with 1 nanometer, and there are many systems. Look at the combustion aerosol. I mentioned a car. Look at the exhaust of a car. We still burn fuels which generate particles. So these are typically in the nanometer size. Molecule and atomic dimension is 1/10 of that. And again, it varies depending on the gas molecule and so forth. But once I get a stable cluster, it's of the order of nanometers. We are all familiar with this virus that has caused havoc, right? It is suspended in air, it's moving around. In fact, the problem with this was the pandemic resulted because people didn't realize that it is airborne and transmitted that way. So I need to understand the movement of that. That's about 100 nanometers in size, okay, about 0.1 micrometer. Then I come to human hair. All of us, most of us can feel the hair on our head. If you don't have hair, maybe you're wearing an artificial hair wig. That is about 50 micrometers, 50 to 100. And just like it varies depending on the individual, that varies. And then I'm very much used, in fact, I'm in Florida here. It's going to start raining shortly. The water droplet, the raindrop is about, thousands, maybe 100 to thousands of micrometers. So we cover a range of sizes, 6 to 7 orders. And I'm, of course, showing you here the size concept, but they could be different shapes, different compositions. Now, while I'm referring to diameter as a size, many times we use the volume of the particle as a metric, because if I'm looking at a fiber type particle, what exactly is this diameter, right? I can say it's the cross section, but it's better to use volume. And there are many other reasons when I do dynamics. Then your World Cup in cricket, I think, is going to start shortly, T20 or whatever they call it. The cricket ball, when it is flying, that meets my definition of an aerosol. It is football season here. We call it football, but we throw that odd-shaped object. Look at the concept of shape. And then I am, of course, a basketball fan. I used to play basketball, so I love this basketball. These are not to scale, but I can say, in fact, on the right-hand side, I will use continuum physics. If I master it and can apply my equations, I can score baskets all the time. It's again trajectory of a particle. But to us, that's not that exciting unless we are into the domain of sports. We will focus on the smaller particles today, okay? And just another way of showing it, particles come in various sizes, just a different way, naturally occurring. Protein structures, cloud droplets, human hair, atmospheric aerosol is everything present floating around and so forth. Okay, so you get a range of sizes. And this is important when I try to understand the dynamics of these systems. So many fundamental steps. I'm going to introduce now nucleation, condensation, collisional growth. I mentioned size. There is a time scale. And then I want to use a mathematical model to describe it. And I also want to solve these equations to understand what's happening. So let's dive in a little more. I just plot the size and time, and I'm going to show you what can happen. While I said the particle is a cluster of molecules, these molecules can come together and form my particle. So I'm really interested in where is my particle coming from, right? How is it formed? And this happens in the atmosphere all the time. It happens in engineered systems. They could have different compositions. So the cluster formation and growth, I really need to understand that. We sometimes refer to that as nucleation, and there is a certain time scale right, associated with nucleation, more towards the shorter time scales. And it could be milliseconds, it could even be microseconds. So depending on the system, I can move from a molecular state to a stable cluster state rather rapidly. Let's keep going. Once I have these little clusters, they can collide with each other. Remember, the gas molecule is colliding with the cluster, causing it to move. At this stage, the cluster is small, so they're moving rapidly. We call that Brownian motion, diffusion of the particle or the cluster, and they might collide with each other. Some of the molecules might actually deposit on this cluster and then grow. So this will increase the size. We call it condensational growth, collisional growth, and there are certain time scales. And this is just a qualitative representation. And now the equations start getting a little more complex, but not that much. There are two regimes. That's why you have two equations. You can see that the time constant for coagulation is inversely proportional to this number concentration in either regime, right? So the more the particles I have, the shorter the time for collisional growth. Again, qualitatively makes a lot of sense. And then also the condensational time, it depends on the vapor concentration or the molecule concentration. It depends on the number concentration of the clusters and so forth. So I can do this detail. But then after this, what happens? I'm very interested in my particles. I might deposit them. I might make very fancy structures. And each of these has an application. And this part of the field has been extensively used. It's called gas phase particle synthesis, maybe, if I'm in an engineered system. But the use of particles is so prevalent, either it be some sunblock or your makeup or a paint or a semiconductor. There's a big semiconductor movement now. Even in India, we want to develop this kind of supply chain process, and you'll be surprised. It's made by these gas phase techniques and many applications. So that field really is very prevalent. But I would say that in addition to the environment, the atmosphere, this field of making particles is a very fascinating area. Okay, I can then look at in little more detail. There are additional phenomena like sintering, and there are different scales I have to deal with. So I'm in a very qualitative manner indicating the complexity of some of these processes, different time scales, different size scales that we have to deal with. So just to wrap it up, why do I even do that? This allows me to really enable applications, right? For example, a lot of work going on in India on the impacts of particles on climate. It impacts, monsoons. It impacts the temperature, atmospheric temperature, which has then a wide impact. So that is one. It impacts me as I'm inhaling these particles, walking around. So my immediate health is impacted. But then I come to these other disciplines. The same knowledge I can use to make materials. I can use to make a solar cell. Right? We often question ourselves, how many of us have photovoltaic panels on our roofs? Very few. Why? Because it's expensive. But if I can develop a low-cost aerosol process or a new material and then just deposit it or paint it on, which becomes a solar photovoltaic device, power to us, right? Many of us will be having these on our roofs. It's used in agriculture, delivering pesticides and nutrients and all kinds of commodity partners. So I'm going to delve in a little more and talk about this. So let's move now to a mathematical form of this equation. Often it's called the general dynamic equation. And I'll just point out the complexity in trying to solve this. So the first thing is I write a balance equation. And of course, for us here, I noted some of us are in the United States early, but this is a wake-up message here. So N of Vt I will use the volume of the particle as my size indicator. And there's something known as a size distribution. This is nothing but a number balance, right? The change in concentration or the change in the size distribution function with time depends on how these particles move about, right? So the second term here is basically the transport term. It depends on the velocity of the particle. I'll write down an equation for that. And then this dynamic process, which alters the size distribution, right? There are many other things inbuilt here. So this is a compact form. I have not included the nucleation term, the condensation term, but those can be readily added on as the particle formation, which means that will also change the size distribution function. So continuing, what is this particle velocity term? It depends on the fluid velocity. There might be convective motion, and this is dimensionless. And of course, there are complexities. Where does this equation come from? We can derive it, but the particle could also move due to inertia. This is the interaction of the particle with the flow field and maybe the altering flow field and the inertia effects. It's the ratio, the Stokes number is the ratio of inertial forces to what we refer to as drag forces. Then the diffusion concept, which I described, molecules bombarding the particle, maybe gravity effects. If I talked about the moon, gravity on the moon is a fraction of what it is here. So that's an impact. I can't just use results from here to apply to the moon. And then temperature fields like thermophoresis and so forth. And remember, I've moved from the particle diameter to the particle volume and doing the balance in terms of that. So of course, a lot of details in this equation, but we'll just move ahead and say that, okay, this is a given form. So let's see, how can I solve this? Going back, what do I mean by solving it? I want to know the size distribution function. So the concentration of particles at every size at any time. I could also bring the location in, right? And that's sort of built in here, but let's presume let's focus on, I want to know the concentration as a function of size, which is the size distribution function. So what does that mean? So at every size, I would like to know the number concentration, right? It's simple. But how many sizes do I have? Remember, we have a range of sizes to deal with. And I just show you an example. Let's say my size range is from 1 nanometer to 100 nanometer, right? And the molecules are 0.1 nanometer. This is just illustration. So I change it to the volume. So the volume of a 1 nanometer particle, assuming it's a sphere, is 0.5 nanometer cube. 100 nanometers, 500,000 nanometer cube. The volume of a molecule is 0.005 nanometer cube. If I want to know the concentration at every possible size, remember this molecule can come and land on this particle, and the new volume would be this plus the volume of a molecule, right? So I love that because particle volumes are additive in most cases. There could be some complexities, but diameters definitely are not additive. And I'll just assume for this simplicity that these remain spherical. So let's say the particle volumes are additive, and even if they're not spherical, the volumes indeed are additive, right? So how many sizes do I have? This is known as a discrete representation, the most accurate representation. So I take the final volume minus the initial volume and divide by the volume of one molecule, because that is my step size, right? And just doing this, look at this. I have to solve 10 times or 10 to the 9 number of equations. Even the fastest supercomputer, this is going to take some time, right? And then just imagine the complexities. That equation was an integral differential equation. There are numerical complexities. So it's not easy to do that. So what do? We need some techniques to really make this thing simpler. And there are a whole slew of techniques. I can start with molecular models. I just look at a few sizes. Maybe that's discrete. There's density functional theory, molecular dynamics. Then I couple with my aerosol dynamics model. I talked about the discrete model, but we try to use sections. And then I want to couple with transport, look at applications, and so forth, right? So again, I can't, of course, talk about all these, but just to give you a few references, even many from our own group and others, there's a whole community in the aerosol field that just focuses on making these models more efficient, making them more distributed, connecting to specific applications like with chemistry, with climate phenomena, with aerosol reactors, and so forth. Okay, so I'm of course just going to leave it at that, but let's look at a new thing which has become sort of a buzzword. In some sense, this was always being used. Everyone is talking about artificial intelligence, algorithms. I really want my computer to be a partner, to be somewhat smart, to learn, and so forth. So it's basically a learning technique. Just like you and I learn, here the machine is learning, and can it help us overcome these complexities? So there is a concept of neural networks. Nicole Reamer at Illinois has done, these are initial steps. Like you look at the publication dates, very recent, including our own group. And here I should point out, I'm collaborating with a professor at IIT Bombay in chemical engineering, Professor Goody and his students. And that's another thing I would encourage ISTA to get into, is the research groups to connect our students to different organizations globally. There shouldn't be, just like I'm sitting here in Florida, Miami, I'm giving you a talk. Had to wake up a little early, but that's no problem at all. But we should be connecting people. So it has been fascinating working on a physics-driven machine learning technique. So I'll just give you the algorithm again and maybe just one result. So what are we trying to do? I have an initial size distribution, right? And I want to know the final distribution. Now I can take every discrete size, but the complexity in that is tremendous, just representation. So I will use integral properties, the total number concentration, a geometric size, a geometric standard deviation to describe my aerosol. So I end up with 3 parameters. I want to know the final 3 parameters. The sectional model is one of the, I would say, a practical approach, somewhat accurate, has been extensively developed over the last 30, 40 years. I can use that to train my machine, right? To train this computer. So I brute force run. Look at this. We've run this. And again, kudos to the student, 60,000 times, because there's also a time factor, right? This depends on the time. On the reactor, we've kept it simple. It's a simple aerosol reactor. Initial distribution, final distribution, depends on the time, but run it 60,000 times. Make the computer do it that many times. And you can see that then I can relate the initial distribution to the final one. What do I do with this? I use this as my training set. I, of course, presume that my sectional model has been run well. I ensure that the accuracy is the highest. That's my baseline, assumption also maybe in some sense. And then I begin to train. So I have input conditions, I have the output conditions. That is the input to my model. And there is a matrix phenomena, which basically relates the input to the output. And I can't just do it with a single matrix to relate this input parameters to the output. I might have layers and several layers. So that itself is complex. And that's why we call this a neural network. If you look at the neural system, there's a lot of branching and our brain somehow thinks that way. And now I'm trying my machine to be somewhat smart, but of course to train it. So once I have trained it, I have these various matrices. So I can go from, by using matrix multiplication from the input to the output. Okay, that's all this is. And of course, a fancy term like artificial neural network model would be used. but this is one way of using a machine learning model. Now that I have this, I want to say, give me any size distribution, give me a time factor. I have these matrices, I can do matrix multiplication and come up with the final result. Okay, so sounds simple, lot of training, lot of computational horsepower goes into this, but in some sense, I see that the error may be significant. So I try to break down the time. I take time steps of tau coagulation. This is where the physics-based knowledge is extremely important, right? I'm of course skipping through all the details here, but I then use a time constant and do that over different time constants and keep doing this. So I would do it for one time constant. If I haven't reached my final time, I use this distribution with my model and keep going till I've reached my final state. Okay, and there's a nice publication out. I encourage all of you to see it. And this will happen more and more. And we want to see more developments in the literature. So I show you some comparisons. The dots are the sectional model. And I've said that's my most accurate model. That's what I'll go with. If I use a log normal approximation, some of you might know the moment approach, I get that dotted line prediction. So you can see there's a difference just with the collisional growth phenomena. But if I train my ANN or neural network well, it agrees well with the sectional model. And then I can look at how much time is required. A log normal model really doesn't need much time. In fact, much less than the ANN, right? But the sectional model takes forever on a relative scale. And the errors are also important to note because ultimately I want an accurate prediction. So these techniques are going to come in a bigger way. There could be more training, but I'll point out that the physics-based approach would be extremely critical in coming up with practical systems that we can use. Now, I have based it on a sectional model as my basis. You know, if I go to industry, I told you that particles have been made for many years. And one good example is titanium dioxide. It's used in paint. It's produced in millions of tons per year, okay, millions of tons. So these people have been running these reactors. They didn't know machine learning. They didn't even know aerosol physics, but they had that practical experience, right? So that knowledge could be used. So I can use experimental data to train my machine learning models. And that's another way that we can bring these concepts in. And now I can really have real data. So it's a data-driven approach in some sense that we use. And there are many applications. Nicole Riemer that I referred to as the first paper she used for atmospheric systems because that's our interest area. Okay, having all of this, let's move on. And I want to now just give you a snapshot of applications. So you see that all this, knowledge, this computational approach, I really want to make some use of it. I mean, sometimes we are academics. Let's just do it for fun also is okay. But we are always driven by an application. And the field of aerosol science is so fascinating. And the applications are immense. And I'll just give you a whole range later. But let's delve into details into two areas. So the first is a wearable sensor. Now, you walk into any aerosol lab. You see many fancy instruments that can measure what I did by a model. We can actually measure, right? And these are mobility-based techniques. There are optical techniques. That's great. There are techniques by which I can also know the composition in real time, mass spectroscopic techniques. But these are all fancy equipment. It's nicely kept in my lab. It's calibrated. Yes, that's great. I have these tools. But what does it mean to someone on the street, right? Or if I'm being impacted by air pollution, or I am an asthmatic and a particle cloud will just create an asthma reaction, and that could be sometimes even fatal, right? Or over time, I want to be sure, I travel all over the place. I might go to a polluted area. I want to know my integral exposure. And then we are so familiar with the pandemic, right? I always wore a mask. I hope most of you did that. Now, of course, we have the vaccine as an antidote. Hopefully it is protective. And most of you are well protected, but nonetheless, there are always these outbreaks. And how do I know I'm safe? If I had a little sensor which gave me a signal, I would be careful, right? And some people, the elderly, they are impacted. So let's look at the snapshot of instruments now. I hope you can see the screen. My screen is a little blocked, but these are miniaturized. So there's a spatial scale and an inverse time scale. You know, the good old filter sampler still used, relatively inexpensive compared to my mobility instrument. You know, I go it or put it out, I run it, I collect the filter 1 day later, I weigh it, I find the PM concentration, I can do a chemical analysis. Then we made these things real time. Many of these are distributed all over India now through your state agencies. The dust track sampler, it's a little more portable. I can take it around. The SMPS system, expensive. I definitely can't move it around as easily. And then this is what I really want. A couple of my students are running this company called Applied Particle Technologies. They are doing fascinating work. Okay, so they have miniaturized some of this. It's an optical sensor. And on the right-hand side, you can actually clip it and wear this sensor. So a lot of developments in this field. And even in India, I know many of you are working with some of these, so one can deploy some in large numbers, whereas I can have one SMPS system. Yes, I can move it around to cover different regions, but something like this will go with the human being, right? And that's the concept of personalized medicine. I'll show you a system drawing later on. Let's see, what can we use it for? We want to send it to the moon. You know, the United States is getting ready to send people onto the moon. 4 have been selected. They're in intense training, and we wanted to keep them there for 2 weeks to show that they can survive. And from there, eventually we want to send, of course, not these people to Mars. We want to bring these folks back alive. The lunar dust is a major problem. The period has been cut down to 1 week. We will keep them there for 1 week. Look, staying in a vacuum environment for 1 week. So we need to build an enclosure. We need to know how to, I can send my SMPS system. It won't even work because there's no atmosphere. I need optical techniques maybe, or electrical techniques to measure this. Then I can combine satellites with these sensors. We took data from 4,000 of these sensors, 4,000 in Taiwan, right? And this is an image of the country of Taiwan with the heat map showing the distribution of PM. China, there are 200,000. India, I think, is maybe in the 1,000. The United States, maybe now in the tens of thousands. This is right, just distributed. Very nice test in New Delhi and real-time source apportionment. You can create a heat map, and all this could be in real time. I could put it on a drone and move it around. I could put it on a robot. Why would I do that? We suffer from wildfires a lot here, and wildfires are very problematic. I can't send a firefighter in, and I need to protect the firefighter. So there might be a path which is low aerosol concentration, and the robot can map that out with the sensor. So many interesting applications, but are these sensors any good? We need to calibrate them, right? And there's always concern. Yeah, it is low cost, it's small, I can deploy thousands of them, but are they any accurate? It's extremely important as aerosol scientists. We not only calibrate in the lab, but we also develop techniques to calibrate in the field as I deploy it. So all of us might be wearing a sensor. I can readily get the data using a cloud-based system, but I can run some calibration algorithms, and I can then tell you, is this working well? Is this not working well, right? Of course, it depends on what size distribution it is measuring, what is the composition, the refractive index, optical properties, right? And then with large data systems, I want to develop algorithms. Again, I'm not going to talk, I'll just focus a little on the lab calibration. So in the lab, I would create a simple setup, that good old box filled with particles. I would generate particles, put them into a box. I'll place my sensor. I'll use the fanciest instrument because I'm in the lab and I can get the accurate size distribution. And then I will see how my sensor is also measuring, right? Is it really correlating? I can change the type of particle, silica, sodium chloride, carbon, sucrose, because the light scattering properties also depend on the composition of the particle. So here I can put in many sensors and just to look at one data. So on the y-axis is the sensor signal, and on the x-axis is the SMPS mass concentration, right? And the SidePack is a commercial instrument. Sensors now are also becoming commercial. But you see, I would like a linear relationship. The first thing to note, depending on the type of particle, the calibration factor is different. The second thing to note is after a certain point, the calibration goes haywire, right? It's too much concentration for this small sensor. So you have to do very detailed studies. It has to be quantitative. Can I come up with an expression for the calibration factor? I want to bring in light scattering principles to understand this better. So some of these publications from a few years ago have already addressed this. And then in real time in the field, I want to keep also calibrating these systems. But the key thing to note is it is complex and I can always deploy a sensor, but it might give me some garbage data or something totally irrelevant. So to get accurate data, and there might be some compromise because these are not as fancy as a lab developed instrument, but as long as I understand that and I can use it, these have tremendous value. Okay, so extremely important to go step by step. And this is our data from New Delhi. We did this, I think, 4 or 5 years ago now, and we put in many standard instruments. I think there were 24 sites where we had these sensors. It was a cloud-based network. The goal was to see, firstly, how accurate these are, how do they relate to the composition, and then secondly, does it give me some information on the air quality status in New Delhi, right? So this work was done very extensively. Of course, a sort of focus study. And here is a result, again, a complex graph, maybe too much detail. I'm plotting the PM concentration over the different seasons on the left-hand side, and I'm attributing it to different sources. So by developing some algorithms, I can also maybe do real-time source apportionment. Of course, there's tremendous variability, but look at the power of this. I don't have to collect data for 6 months and then do it after the fact. This is on the fly. And you see there's a lot of seasonal variation. Some of this is only as accurate as my source profiles. We've, of course, taken it from the local literature and the literature, but we can do that. And then we can do certain episodes. We often hear, oh, folks in the neighboring state are burning things. Diwali, crackers are going all over, right? So there are certain days or periods when we have these episodical events, and then odd even license plate for driving. Delhi was trying to control that. Does that really have an impact, right? So we can study these, we can then enable the policymakers. So a lot more has to be done. While the academic community is doing it, I know a lot more studies are now underway in Delhi, but really a link to the policymakers and application and really to see. So for example, if a certain season, let's just pick the secondary aerosol is dominating, can I control that somehow? Or if the biomass burning, can I really show that this is the true picture, reduce it, and to see if the contributions are going down or the PM levels are going down. So that is much needed. It's a tall order, maybe sometimes easily said, but we need those partnerships to do things. The other thing is I really want to have this heat map concept, and companies like Google are now doing this. If I want to buy a house in California, they'll give me a heat map. In this region, the air quality over the year, it goes up, goes down, but that region is very clean relatively. And, the real estate people are increasing the value of those homes. So how do I use, there is a concept of kriging. It's a statistical technique. By measuring at so many points, I can find the concentration at a desired point. But do they account for the wind direction, the wind speed? So we modified some of these techniques to account for the wind speed and direction. Because if it is, the wind is coming as shown on the right-hand side from the top to the bottom, obviously the sensors at the bottom won't impact the level here, though they are close by, right? So I shouldn't use these to calculate at point 0. Whereas 1, 2, 3, 4 might dominate more. So this is the guidance we use, and a nice technique that was developed. Of course, there are all kinds of kriging techniques. Now I'm trying to create a whole map of concentrations. I won't go through each of these. Linear is very simple. Exponential has more terms, but you can apply this. We applied it to the North China Plain region. And very polluted region. And you see that if I use ordinary kriging, and these are just different kriging models that I described, you see that it's very limited in its prediction. Whereas I bring in the wind speed and direction, you see a much greater spread, a lot more accuracy, hopefully, with respect to the PM concentrations. And but very different, very, very different. So one has to really account for things like wind speed, wind direction when we create these heat maps. Okay, and the techniques, of course, the details are in the paper. I'll just pause here now. I'm running out of time. This is a fancy picture. Every one of us should be wearing a sensor. It's low cost. I can clip it just like I carry my cell phone. I can put it on a drone. I can put it on trucks. I have satellites looking at it. Physicians will look at my data. What am I being exposed to? If I'm a concerned patient, they can tell me, hey, better be careful, put on your mask. Personalized medicine is a new field which combines it with the genetic behavior of an individual. So it's really personalized, because you and I may be very different. I might be more at risk of a cardiac event, then the levels would be very different. It depends on my genetic structure and so forth. And then all kinds of people are coming into this. So it's a very fascinating field, concept of smart cities, citizen science, combining all of these, using the existing network to do it. Very quickly, I want to jump and look at a climate effect, carbon dioxide. Everyone is talking the climate is impacting. In Miami, we seem to be going under the water. In United States, I'll be frank, many people don't think climate change is even real now. But in Miami, everybody knows it, because my beautiful homes by the ocean, I can see the sea level rising. So what do we do about it, right? So I can't just say climate change is happening. Yes, I need to understand it better, but now is the time for action. So I have to reduce CO2. And the concept of circular economy is coming in, right? What type of fuel do I use? How do I generate power? I can say solar power, but is it going to meet all my energy demands? I also make products. They have a carbon footprint. Can I use better precursors? Can I capture the CO2 and recycle it? Very challenging. And then you see this car, it is flying, it's elevated. And this is, of course, a garage in a home. Due to traffic jams, it takes forever. It's so inefficient. So this is electric propulsion. So Miami is a test bed where cars are going to start flying. I mean, this sounds so futuristic, but it's happening. And all kinds of exciting things. And we as aerosol scientists need to step up. If we can make materials which can trap and convert the CO2, it's extremely energy intensive. I'm going to go through this very quickly now. So please bear with me. I want to use solar energy to provide the energy. I don't want to burn more coal or gas. natural gas to get the energy to reduce CO2. I want to use solar energy. If I look at the solar energy field itself, I talked about it. I want my roof to be coated with an aerosol process and converted to a solar cell. Okay, so there are many aerosol concepts here itself. There are aerosol phenomena in industrial systems which capture CO2. The amine processes, which many chemical engineers are so familiar with, has an impact of fine particles. I can develop systems next to a petrochemical plant which will take the CO2 as a feedstock. Just going through these very rapidly, but I just want to quickly allude to a novel material, graphene, which can really provide me a support for catalysts to convert to the CO2. If I use graphene sheets, it's extremely high surface area. I want to promote chemistry, chemical reactions, but then they stack and I lose the surface area. Instead, if I can put these sheets in a droplet and then aerosolize it and crumple this, then I retain most of the surface area. There's a little drop, but unlike the sheets, I get balls of graphene. The beauty about this is I can also add the catalyst and get in one shot, a single step process, a material that I can use. So it's the crumpling process. There's very interesting physics of evaporation and crumpling. And I know I'm really taking too much time here. Just bear with me a few more minutes. When do I take a sheet? It's like taking a piece of paper. I can apply force and make a ball of paper. This is exactly similar. Only thing, I'm not taking this graphene sheet by my hand because it's so tiny. I'm putting it in a droplet. As the droplet evaporates, I put the evaporation really puts a crumpling force on it. So I do the analysis, aerosol phenomena to study evaporation, crumpling phenomena. It's of course now a little bit of mechanics, and the density of a crumpled structure is related to the crumpling force, right? If I apply more force, I'll get a small ball of paper. If I apply less, it will be bigger. It depends on the size. And I can relate the crumpling force to the particle size and some of the process parameters. I will do this in an aerosol process. I'll keep some things constant because I really want to understand the confinement force as a function of the evaporation rate. So I map out a region where crumpling will take place, another region where it won't crumple, it will just ripple the sheet of graphene, but this is my desired condition. So I need an evaporation rate accordingly. And of course, I can vary the temperature, the size. So you can see how aerosol physics can be used to design a crumpling process. And then, of course, I want to check, is it good to convert the CO2? I add the TiO2 as the photocatalyst, and we get fabulous results. I map it out. And here I'm showing the end product because once I get carbon monoxide, I can drive the chemical processes, chemical industry established processes to make products of value. This is now becoming so important that people are trying to remove carbon dioxide from the atmosphere, dilute system. This is desperation, and you'll see huge systems at the back of our engineering building. We don't want to put such a big system, but a smaller one so we can study it, we can make useful materials. So this is the concept of circular economy, and direct air capture is a very hot topic. Aerosol science is really going to drive it because how you make the catalyst, how you deposit it, how you use it is going to be enabled by this. So with that, I will pause. Thank you for listening. I know I have gone a little beyond my time, but I hope you got a snapshot all the way from fundamentals to applications. We can really promote this. This is a picture from a few years ago. Even at a time there have been so much excitement that undergraduate students come and work in our lab, and it's just been a fascinating ride. And I hope to keep going, interact more with IESTA and others. And thank you for your attention. Right.
Thank you. Thank you so much, Professor Vishwas, for such an excellent and informative talk. I admit that I have learned many things from your talk today. There are many things which were new for me. So thank you so much for that. And I'm sure there'll be many questions. So what I would request to audience that please raise your hand and I will call your name one by one. You can directly interact. In case if your mic has some problem, you can type it in the chat box and we will read it out. So now people can raise the hand and we can go for the question answer session with that. Yeah. Anyone? Okay, so Professor Devara. Yeah.
Yes. Professor Pratim, really it is a very exciting and thought-provoking talk. All along I forgot my time. Even though you felt that you are boring or exceeding the time, I did not feel at all. So actually I don't call them as questions, just I wanted to call them as clarifications. So one of my clarification, I will start from the end of your talk. You have talked a very important thing, CO2 sequestration and then conversion. So I have been going through that literature, and then of course I am trying with my colleagues here some work. During the process of conversion, I had and then I experienced many toxic gases emits. Say for example, methane.
Yes.
Is there any combating or mitigation methods to avoid or to suppress that type of gases? One way we wanted to gain out of that process. The other way, unknowingly or knowingly, we are polluting the environment.
Right.
So methane, such an important gas, which is very much responsible for warming and all. But of course, how to avoid? Either in a simple way, not involving very much thought about circular economy and all. Either in a simple way. That is one thing. Another thing is just I will finish one more small question. Of course, you have rightly talked about IA and ML techniques. Of course, they are revolutionizing the entire science, not only aerosol, anywhere. But the thing is, I have the gut feeling that even those techniques, even though many people are proving the results to the near accurate and all, but unless your input distribution or data sets are very accurate, your forecast also, your prediction also equally accurate. So, and one more thing, just like we were doing way back, cloud seeding experiments. So whatever experiments you do in the laboratory, they are not hold good in the atmosphere. So how actually your laboratory testing of these techniques will help ultimately in dealing with the atmospheric aerosol? These are the two of my simple questions.
Yeah, no, good, very good. Thank you for those questions. So I'll start with the first one. You're absolutely right. I want to develop a process for converting CO2, but I don't want to end up with other byproducts which would be problematic. And this is extremely important. So, and this is again where aerosol chemistry comes in. Some of it we study in the atmosphere, the chemistry on aerosol surfaces. In this case, it's very similar. It's, of course, an engineered material. The good part is I can control the characteristics of the surface. And this is true for any application. Even if I'm using it to deliver a drug, I have to be very careful. But talking about CO2 photoreduction, let's just pick that. The chemistry, of course, this is a very simple chemistry connected to the band gap of the semiconductor material. And you see that I'm producing carbon monoxide. The reason why we stop there, because CO plus hydrogen, it's known as syngas, is an established precursor in the petrochemical industry to make things like nylons, plastics, and so forth. Okay, so in some sense, that's what we do. But do I want to end up with an aldehyde or aromatic compound. I could do that. Of course, it would require. So controlling the, electron either pickup or giving out electron processes is extremely important. So the fundamental chemistry really drives it. Where does it come back to the aerosol part is by that relationship, I will then tune the properties of my nanoparticle catalyst to get my desired product. So, but this is a very important point. We need to look at this holistically. And again, I just rushed through. The message is the connection back to the aerosol characteristics are extremely important. Okay, the second question is also an excellent one. We calibrate in the lab. Yes, that's good to do. Anytime we prepare a device, we should do it. But how well is it doing in the field? So some knowledge of the field conditions is also important to calibrate in the laboratory. But going to the field, you mentioned AI, ML, these data systems, it depends on the quality of the data we input. So you'll be very surprised, like I'm getting these large data sets. If you look at our paper done in Taiwan with 4,000 sensors, many times some of the sensors have gone bad, right? How do I even know? There again, we use machine learning techniques to pull out the faulty data. Many times there is a gap in the data set. We might use a machine learning algorithm in a narrow manner to fill in the missing data. So there are many approaches, but a machine learning algorithm will only be as good as you said, your data set, your algorithm itself. So you have to be very, very cautious. But overall, the field calibration concept is extremely important. Coupling it to satellites, coupling it to stationary monitors. There might be fewer in number, but it's an extremely important thing to do. But there is a capability to do that. And that's the beauty of these techniques, right? And the system can then become smarter. I don't know if I'm not an expert in AI, but there is this field of generative AI where the system itself learns, right, from the data sets and so forth. That is one, but you need humongous supercomputers to run these codes. So it's really not feasible. That here I'm minimizing my sensor, but then I need a supercomputer hooked up. It's probably impossible. The other concept is federated learning. Concept of edge computing, which means at the edge on my cell phone, I want to be running algorithms to do some of this. Obviously, it can't be, I don't need a huge supercomputer to run this. So it's a very fascinating field. We clearly have to work with computer scientists together to have robust algorithms. So hope I gave a broad answer, but exciting field, very relevant questions. And yes, have to be very cautious as we apply these. Yeah,
Dr. Rajat Singhal. Yeah, Dr. Rajat Singhal has raised the hand.
Yes, sir. Can you hear me?
Yes, please go ahead.
Sir, can you explain to me the little bit on real-time source apportionment? Because I was doing source apportion models previously. I could not understand what you mean by real-time.
Okay, so if you... So let's say I have this network of instrument sensors and so forth, right? And you're wearing one of these sensors and walking around New Delhi, and just pick New Delhi, right? So when I say real-time source apportionment, I need to have the source profiles. So in the Delhi airshed, there are all kinds of sources. So I have to have some knowledge about the source profile. So many people have done studies and so forth. Sometimes it's complex because the source characteristics change. So I use, based on my real-time PM concentration, real-time composition of the particles, right? And my heat map concept, I get the distribution that I am at a particular instant, right? So I'm doing traditional source apportionment, like let's just pick chemical mass balances on the data in a real-time basis. So as my sensor is collecting the data, it is providing an input maybe to the cloud and sending back the information and giving me a graph like this. This is, of course, averaged over seasons, but this is an episodical thing. So that is what we mean by real time, right? So I'm not averaging out the data, but I'm doing it on an instantaneous data set. Obviously, there will be a lot of variability. There will be, the variation. We have to account for that. It also depends how good the source profiles are. So in some sense, I'm just constantly doing the chemical mass balance calculation. So I hope that is clear. Of course, like a good professor, I'll say, please read this paper. I know Jaiprakash is here. He actually did the work. So you could also email him later. And if you have any questions, but there's a series of papers which outline some of this recently, last few years. So I'd encourage you to see that for the details. I hope that was a little.
Right. Thank you very much, sir. Thank you.
Okay. Dr. Abhijit. Yeah, Dr. Abhijit.
Yeah. Thank you, Professor Biswas. Myself, Dr. Abhijit Chatterjee from Bosch Institute, Kolkata. So my question is to you that as graphene can will be used as a for capturing carbon dioxide directly. So I have read some of the recent studies, maybe 2-3 years back, that carbon dioxide can also be converted to graphene. Okay, so can that be used as a kind of recycling of graphene, because it is actually absorbing the carbon dioxide, and the same carbon dioxide can also be converted to graphene? So I don't know. I mean, what's my question is,
no, this is very good. This is the systems analysis. Going from carbon dioxide as the precursor. So you see this here, this arrow, other carbon-based products. We all complain, reduce the carbon footprint. On the other hand, we really want to use carbon in any battery system. I know electric vehicles are coming. There is a carbon-based electrode. Just imagine the quantum dot form of carbon has so many different applications. Is CO2 the right precursor? Maybe a little more challenging, but you're absolutely correct. It becomes challenging. I have to provide another carbon source because of the energy intensiveness to go all the way down to carbon. So from CO2, if I can go to CO plus hydrogen, that is synthetic gas, I can make a lot of other carbon-based molecules, complex carbon molecules like nylon, plastics and things like that. If I want to come all the way to carbon, it becomes very energy intensive. So it's challenging because we talk about circular economy. We have to keep track of the economic feasibility of these processes. But you're absolutely right. It's being used. And you look at these precursors, I might not start with CO2, but I might start with other carbon-based materials. Like when I make paper, I end up with lignin as a complex carbon molecule, and that is basically a waste, right? We burn that and produce CO2, of course, as a result of the combustion. Instead, if I could take lignin and make graphene, make carbon dots, make battery materials, this is right. So this is the sort of new concept in sustainability where we are bringing some of these in. But you're absolutely right. Some will be practical, some will not. But any value-added chemical, firstly, reduces the overall carbon footprint. So it's a good point. And graphene that I'm familiar with are more other carbon-based sources rather than CO2. But there might be some academic papers for sure on that going all the way also.
Okay. Can I ask you a very naive question from your initial part of your talk? Actually, I thought about this multiple times, but I couldn't get the right answer. Our research also in literature I could not find. So when we are talking about the aerosol definition, we say aerosols are liquid or solid particles suspended in the air. So why don't we consider cloud as a part of aerosol? Why? Means clouds are separated from aerosol? Because in principle, clouds are also fulfilling all the definition of aerosols.
Yes.
So what
Oh,
makes
very
it
much
different?
so. I know sometimes they say aerosol scientists want to say everything is an aerosol problem. So cloud to me is definitely a cluster of small particles suspended. And, there's a whole field of cloud physics, cloud chemistry, and that's another community. But to us, they're all aerosol scientists. And to me, that's very much so. And there's some fascinating work going on even at my university. We have a very strong atmospheric science department with some fabulous cloud physicists. We have, of course, integrated them in and given them the label of aerosol scientists. And much of the phenomena is, aerosol type phenomena and a little more complex maybe in terms of clusters. So to me, a cloud is definitely an aerosol.
Okay,
It is a suspension of water droplets.
Right.
It could be ice particles too that are suspended, right? And around it, So that to me is very much so.
Okay,
And,
thank you. Because I was thinking the
Right.
same, but I had some discussion with some senior people, and they were saying that clouds are different. And they said
Yeah.
there is some literature, but I never found any literature which can differentiate cloud and aerosol. So thank
Right.
you for that. And one more
Yeah.
thing, which is
Can
not a
I ask
question.
a question? Okay, sorry. Yeah.
Yeah, can I finish? Yeah. Yeah. So second part is related to your sensor thing, low cost sensor. So you were talking about the sensor, then you said that it is calibrated in the lab. Oh, somebody is talking in between. Yeah.
Yeah. Okay, please
Okay.
go ahead.
So when I was talking about when you were showing about low cost sensor.
Yeah.
So whenever you are calibrating, you must be putting some mixture of some composition. You are presuming this is the composition, and because as you indicated that optics depends upon the composition. For
Yes.
different type of aerosol, it will be different.
Yes.
So whenever we are using sensor, so I think we can make the sensor with respect to different composition, and then you should know that where they are going to be deployed, and those sensors should go to those places so that they are giving relatively more accurate results.
Yes. So yeah, this is a very good point. When we calibrate in the lab, we do it with a pure aerosol. Yes, I can mix the aerosol. But if you look at I'll specifically point out, I think this paper has, so the light scattering principles, typically in the Mie scattering regime, depend on the refractive index. So how do I come up with a complex expression for a refractive index of a mixture of compositions like you're pointing out? Will that even work? So sometimes it works, sometimes it doesn't. So, but very important point, because in the atmosphere, I have a mix of particles, but we can also integrate, right? And sometimes sort of use that integral method to invert the data and this thing. So it's very complex, and the Mie equations are extremely nonlinear. There are a bunch of Bessel functions. So the inversion process is also very challenging. But in a certain range, like I need to have some pre-knowledge. Let's just put it as you said. I need to have some pre-knowledge of what is the particle in that atmosphere and try to then propose a calibration algorithm, right? But very good point also. Yeah, and not easy. And that's why some of these are not as accurate as in a laboratory study. So we have to be very cautious. Yeah.
Hello, I am Maya here. Niraj sir, can I ask a question? Is there a time?
Please, sir.
Hello, Dr. Biswas. Thank you for a very inspiring talk. I have a very brief question. This is regarding the lunar dust you mentioned.
Yes.
Well, we don't even know whether to call it an aerosol. It may be a vacuosol or something. But nevertheless, I was quite interested about your idea of sampling it. Can you tell me how do you sample this aerosol? I mean, this system.
Yes.
How do you even
Excellent.
sample? Yeah.
Right. Excellent point. Lunar dust, yeah, we might have to modify our definition. So if you look at the lunar atmosphere, look at the Knudsen number, the mean free path is extremely large. So, the Knudsen number accordingly is very large. It's, the way of seeing it. So it's always maybe continuum, it's ballistic motion. So any technique that I develop has to rely on that ballistic properties of the aerosol. So let's assume the lander, and this happened. If you noted, when Chandrayaan was shown, there's a whole cloud coming in. So these vehicles that at least the United States will be sending will have these sensors on the outside. So as the lander is landing, of course, there is it carries its own oxygen and hydrogen, just to pick those. It's not electric propulsion. Later, we want to use electric propulsion, battery-based technology. But as of now, it's combustion, hydrogen, oxygen. So that jet exhaust really kicks up a lot of the dust. But it is amazing. It's ballistic motion, right? So the sensor has to be placed at different angles. I don't have a picture here, but maybe I should have shown that. Very exciting. So we place a series of sensors on this vehicle, which will then ballistically get these particles, because the particle has to go through the view volume and we measure it. You can't do it with one sensor, so you have to have a whole bunch. So that is one aspect, right? The second is, if I am in, and this was, I had the privilege of interacting with Neil Armstrong way back when I was a young faculty member. And he would tell me that this dust tends to stick. So when they enter the enclosure, there is, of course, an atmosphere there, right? And in that, it's pressurized, so the dust really gets suspended. So in the enclosure, we want to keep the dust out, and I can measure that using a similar technique. But the push by NASA is don't rely on flow. So these have to be electric field driven kind of systems. So you have a little electric field where you might want to attract the particle in. Very interestingly, these particles all carry a charge, and then you can easily design that. Outside, it has to be similar, right? It's ballistic motion. You have to have a whole distribution. And that's why one SMPS is not going to do it. Firstly, SMPS, you need a flow. And even if you have carrying your own gas cylinder for your SMPS, it's not going to work, because you have to rely on the ballistic motion. So again, a brief answer, but extremely exciting and very topical work going on, and no solution known as yet. Several of these have gone on to the space station, which is again an enclosure, low pressure, but there is an atmosphere there. So very challenging, but a lot of exciting things.
Yeah, thanks. Because when we saw the landing and I saw the color, that is the first question that occurs to me. Thanks for touching the topic.
Yes. And by the way, it's extremely important, because all your solar panels, your devices, like, Chandrayaan is going to phase out. It's sending data now. It's all solar driven. When we go to Mars, we'll also have nuclear reactors, of course, but in these cases, they're mainly solar driven. And if I have a dust layer sitting on my solar panel, you can say goodbye to it. And that is a very thing. So they're also using electric fields to then direct the dust away, not only measure, but direct away. And the human health aspect was extremely important, which even Neil Armstrong had detected way back in the first mission to the moon.
Hello, Dr. Devra, just to say hi to you.
Any other questions?
Okay.
I got some hands. I can't see the screen. So if one of you all can call
if you
them.
don't mind, there are some questions by students in chat box. If you don't mind, I will read it out.
Please read it.
Okay. So there's a student, Ankita, and she wrote, if I am having accurate mass concentration and I want to train a low-cost sensor for monitoring mass concentration, then in input, I will put the data from low-cost sensor, and in output file, I will use the accurate mass concentration. Then using ANN model, if I will get the weight factor matrix, then what will be the next step of it?
So the question is
little long.
No, I'm trying to understand. You would use a calibration to get the mass concentration, like I've shown on this graph, for example, right? In this case, on the left, it's a light scattering signal, but I want to convert that to a mass concentration. That would come from the calibration factor. So the question is, what do I do with that? Could you repeat that, please? Just read the question.
Okay, I'm repeating the question. So if I am having accurate mass concentration and I want to train a low cost sensor for monitoring mass concentration, then in input, I will put the data from low cost sensor, and in output file, I will use accurate mass concentration.
Yes.
Then using ANN model, if I will get the weight factors matrix, then what will be the next step of it?
Right. So let's say I want to use the mass concentration to get the size distribution, right? I can then use the ANN type model to relate the mass concentration to a size distribution. I would train my ANN model to be accurate in that region and then have a correlation for that. So that could be one. Or I might want to know, we talked about the moon, right? So the moon might have a health parameter, an exposure parameter. How much is my lunar visitor astronaut being exposed to? So that could be part of an ANN model, taking all the sensor data and saying a health index, right? Because I have to protect my person who's going to stay on the moon and so forth. So it depends on the application, but the key part is what you said, the first part, based on the calibration, like on the left-hand side, I want to take the signal and get an accurate mass concentration. Even that is of value, right? For example, PM 2.5, PM 10, that could be of great interest to me. Even that is, and then of course, how do you use PM 2.5, PM 10, depends on the application, right? Hope I gave a answer the question. Yeah. Anything else?
In one of your slides, you have said that TiO2 is used as a catalyst. Somebody is asking, Puneet is asking why TiO2 is used as a catalyst.
Right. So TiO2 is a wonder chemical, right? It is a semiconducting oxide, and it's extremely important. So maybe I show, let's see. If you see the bottom of the screen, so TiO2 is a semiconductor. When you shine light on it, I want to use solar energy, I said, because we need a lot of energy to reduce CO2, right? It's a very stable compound. The way I want to do is use solar energy. So that is represented by this light quanta h nu. When it falls on a TiO2 particle, it separates the electron and the what we call as a hole, where the electron was initially resident. So it's deficient of electrons. So it creates an electron hole pair. This is the property of a semiconductor. Now, silicon is also a semiconductor, but in silicon, which is what makes our solar cells, the electron really moves away and we produce current. Here, I want to separate it and keep it sort of stable. So it's a wide gap semiconductor, right? So once this is stable, this electron is available, the hole is available to do chemistry. So in this case, I'm oxidizing. In the last one, I want to reduce CO2. So I use 2 electrons to reduce it to CO. So these are all electron hole processes, which is basically fundamental chemistry coupled to this semiconductor. Yes, there are other semiconductors. The beauty of TiO2, it's very stable. It can be used for many, many years together. That's why it's used in paint. Of course, in paint, it is not the semiconducting property. It's the light scattering property that is effective. But it's a wonder chemical. It's used for many photocatalytic reactions because it is so stable, right? And then I have to support it. So the graphene is being used to support the TiO2 and use as a system to reduce carbon dioxide.
Okay, thank you. So another question from a student, Deo Prasad. He is asking, are we still lacking understanding of the sources of air pollution? What is more important now, whether it is research, further research, or mitigation policies?
Right. So you never discount research, fundamental research, and you were also looking at my molecules in a simple way. Why am I even doing that? I'm doing it so I can come up with new applications. But you're absolutely correct. We want to advance real-time measurement. Sensors are one example of doing it. I need to continue to develop it so I can even get the chemical composition in a small sensor. And many people are working on these things now. And these are really excellent developments. But you're also right. How accurate are the source profiles? But if I have good instrumentation, I would also measure the source profiles in real time. So these developments are extremely important. But as I was trying to allude to, in addition to what we do as scientists, we have to connect to the policymaker. Because if the policymaker does not use our results effectively, or at least try to use it, it's not going to improve the air quality. So we need a very holistic approach, and nobody can deny that the air quality in certain times in New Delhi, for example, is extremely poor, and it's impacting young children, it's impacting elderly. In the United States, we had that situation. A lot of this cleanup has happened, but it's not perfect either. We still face that problem. There are a lot of asthmatics, a lot of other problems. So we need to work with the health scientists, the medical folks, the policy makers. But the net is I need to reduce the level of PM, and that's not going to hurt it. Sometimes, of course, people question that too. How clean do you want to go? But let's at least bring it down to a level which is safe for humans. And the World Health Organization already proposes levels. Let's try to meet those levels. And then, of course, the next steps. India has standards too. China has done a very effective job. So also learning from other airsheds where some of the policymakers have implemented and made changes. So that's the overall picture. Yeah.
Thank you. Last question from the chat box. And this question is from Akshit Tada. And he's asking, which method produce graphene from aerosol?
Right. So again, I'm, in a very quick manner going through this. So we have an aerosol reactor. So we start with a nebulizer, which is a very standard aerosol generator. This is, of course, a lab study. So it's a small, very precise nebulizer. You can use a spray system. Graphene sheets are readily produced as a precursor. So we just suspend the graphene sheets. My interest is to get it into a droplet because I want to drive this process and crumple it, right? And I want a single step. You see, this is a single step. I can produce large quantities of graphene sheet. So we start with something called graphene oxide, nebulize it, send it through this furnace to dry it. And this is, of course, a controlled study. I change the temperature to understand and so forth. I could also use dryers and then collect it. So very simple aerosol process, which gives me crumpled graphene. And as I said, if I use the graphene sheets by itself, they will all stack up and I lose the surface area and they're not effective. These graphene sheets are also used to clean up water, right, in membrane processes. Here again, a stacked system will not be effective, but a crumpled system is very effective. And we have also shown that. So this is the aerosol process that we use to make the crumpled graphene oxide material. If you don't have the right conditions, you will rip the sheets, right? Because I want to make a nice ball. And that's why we have to understand and do all these scaling law analysis to figure out a working domain where I can get a nice crumpled structure. Okay, good.
Thank you. Thank you so much. And thank you for patiently answering all the questions, all type of questions. Thank you so much. And now we are coming to the last phase of this talk. And that is the vote of thanks to acknowledge everyone involved in this talk. So this is my present duty. So firstly, on my behalf and on behalf of ASTA, I wish to thank Professor Pratim Vishwas for kindly accepting our invitation to deliver this ISTA lecture series for September month. While contacting Professor Vishwas, I requested him to deliver the talk at 4 p.m. instead of 5 p.m. Actually, our till last talk, our time was 5 p.m. And but many people requested for many practical reasons to change it to 4 p.m. And Professor Vishwas, I am humbly and gratefully thanking you for kindly accepting our request. I know, means we all know that it is your 6:30 a.m. when you started. For us, it is around 4 p.m. But you got up so early and prepared for the talk. So thank you so much for that. And thank you very much for giving us time to give this talk, which enlightened us. It was really very insightful and wonderful. I also wish to thank the effort of BRC team led by Dr. Manish Joshi, including Dr. Mariam and others, who do a great job every time, even means from making flyer to online lecture, executing online lecture. They are doing the main job. And lastly, I wish to thank the whole ISTA team led by Professor Tripathi for their continuous support. And with this, I thank you all. And I look forward to meet you in person sometime soon.
Yeah, so it was a great pleasure. I really appreciated the questions from the students. Keep going, work hard, and it's a lot of fun. And when we have fun, we like to, do more of that. So this is really a lot of fun. So get engaged, continue and make a good contribution. In some sense, we have many challenging problems, and we need the contribution of everyone. My colleagues here, thank you. Dr. Rastogi, Devra, Maya, is noted Manoranjan Sahu, Jai Prakash, and many others who I couldn't see on the screen. Thank you very much for joining. And waking up in the morning, as you said, I had a lot of fun myself. And of course, in person is even more fun. And I look forward to meeting all of you when I visit next time and interacting with ISTA even more. And I'm very excited to learn the renewal interest in ISTA. In some sense, I've been there from day one myself. So when it is doing things like this and active, I really appreciate it. And any help that you need in the global community, I'm happy to help because we are well connected there also. And of course, the American Association for Aerosol Research is a wonderful group which would love to connect to ISTA. And there is an international assembly also, which is very active. So thank you very much. I really enjoyed it. Thank you for inviting.
Yeah, thank you. Thank you so
Thanks a
much.
lot.
We will reach out to you. Thank you so much.
Thanks a lot, Pratim.